So here we have. I'm sorry.
Hello fellow chemistry students. Welcome back to another chemistry video. And today we're going to be doing equilibrium. But before we get started, we're going to switch you to a smaller screen. So to start off this lesson, you have to know what equilibrium is. So equilibrium is referred to dynamic movement or balanced stability. Also, equilibrium is reached at a certain ratio depending on the reaction. And it doesn't always have to be a 1-to-1 ratio. It could be 2 to 3, 2 to 3, 5 to 5, anything else. It could be multiple ratios. And another thing you have to know is Le Chatelier's principle, which is if stress is placed on a system in equilibrium, which would effectively throw off the balance, and then equilibrium will shift to counteract the stress. To continue, if you increase pressure, equilibrium shifts to the side with less gases, and solids and liquids do not affect the equilibrium. And lastly, when you add to one side, equilibrium shifts to the opposite side, and then if you take away from one side, equilibrium shifts to the same side. So here we have our reaction. It's Zn plus HCO is in equilibrium with ZnCO plus H2. So here, if we add Zn, which is right here, there would actually be no shift. Because if you look back, this is a solid, and if you remember, solids and liquids do not impact the equilibrium expression. So if we take away H2, which is right here, we also know that if you take away from one side, equilibrium shifts to the same side. So what that means is that it'll shift to the right, which means equilibrium will shift to the right. So here we have some reaction pathway questions. To even know what reaction pathways is, they are actually graphs that represent collisions. And these humps right here represent the collisions. And this sort of bracket represents the activation energy, which is the amount of energy that it takes for the reaction to occur. So let's start with this question. In each graph, which side is favored? So we know that this has less activation energy, in fact, on the reactant side, so it'll take less time to go here, which will favor the product side. So now in this question, the products, since it's a reverse reaction, the products take less activation energy to create the reaction, which will make the reactants favored. So here we have our K expression, our formula actually, which is K equals products over reactants. And the K right here is always going to be the constant, so it's always going to be in this formula. And just a quick fact, solids and liquids do not belong in the K expression. So if there's a solid or liquid in your reaction equation, they do not belong in the K expression.
Now we're going to move on to some quantitative equilibrium problems. With these types of problems, they usually require ice charts, which are designed to determine unknown concentrations with given information. So here's our given information here. If the KSP for CaOH2 solid is 5.5 times 10 to the negative 6, what is the pH? So we're going to start the problem by writing our reaction, which in this case would start with the reactants CaOH2 solid. And since this is our only reactant, it's going to be at equilibrium with Ca plus OH minus. Since there's a 2 here, you have to balance it by putting a 2 in front of the OH.
We're going to write our K expression. When we write our K expression, we learned from the previous video that K is equal to products over reactants. Since K is equal to our products over reactants, we're going to write K is equal to the concentration of Ca plus times the concentration of OH minus. Since we have a 2 in our reaction in front of the OH, we have to square the OH minus concentration. We don't put it over any of the reactants because, as you can see in the reaction, CaOH2 is a solid, so it doesn't belong in the K expression. After we do this, we're going to make our ice chart. It's going to start with I, which is the initial concentration, C, which is the change in concentration, and E, which is the concentration at equilibrium. We're not going to worry about our equilibrium concentrations of CaOH2 because it's a solid. And since the concentration of Ca isn't given, we're going to put a 0 for this and the same for OH minus.
For our change in concentration, we'd have to determine which way the equilibrium is shifting. If we look back at our reaction, we can determine that it is shifting to the right. So we're going to write plus x, x being the concentration over here, and we're going to write plus x over here. But instead of just writing plus x, we'd have to put plus 2x because if you look back at the reaction, there's a 2 in front of the OH. So then our final concentrations are just going to be x and 2x. After we do this, we would have to equal our final concentrations to the KSP, which if we look back at our given information, the KSP is 5.5 times 10 to the negative 6. So this is our KSP, and it's going to be equal to the concentration of x times the concentration of 2x. Instead of only writing 2x, we'd have to write 2x squared, because if we go back to our original K expression, this is squared. So now we simplify it and we get 5.5 times 10 to the negative 6 is equal to 4x cubed. If we divide both sides by 4, we found the concentration of x, which is equal to Ca plus, but we need to find the concentration of OH minus, which is equal to 2x. So to get our concentration, we would multiply x by 2, and we would get 2 times 0.0111199, and that gives us 0.0222. So this is our OH concentration. If you look back at our problem, it asks us for the pH concentration. So in order to find the pH concentration, we would do the negative log of the OH, and that would give us our POH. So our POH is equal to the negative log of our OH concentration. And looking back at what we just did, our OH concentration is equal to 0.0222. And so when we plug that into our calculator, we get POH is equal to 1.652869. And so if we recall from previous lessons, pH plus POH is equal to 14. So that means we would just solve for the pH plus our pOH, which is 1.652869. And we would subtract this from both sides. And we get our pH, which is going to be equal to 12.4.